And now, please welcome to the stage, Saeed Meherban.
Good morning, everyone, and welcome to this morning's session on random quantum circuits. First, we'll have a long plenary talk, which is composed of two merged talks. First, Nicolas LaRacuente will tell us about approximate K designs from low communication shallow circuits, followed by Nicolas Schuster, who will tell us about random quantum circuits in extremely shallow depth. Thank you very much, and please welcome Nicolas.
All right, well, thank you for the introduction. And indeed, I'm going to start with the Approximate Unitary K designs talk that is joint work with Felix Leditzky. So first, I will introduce the idea and motivation of K designs. You probably recall that quantum transformations are modeled by unitaries on Hilbert space. And at least within finite dimensional Hilbert space, the Hilbert space is compact, and there is a well-defined notion of a Haar or uniform measure that weights unitaries equally. So in the case of qubits, you might even visualize this as rotations of the Bloch sphere. There is a notion of a completely uniformly random rotation. So random unitaries are very useful in quantum information. We see them in quantum Shannon theory, both as random channels and quantum expanders, and as random encodings that are often used to show that one can achieve, for example, a certain rate or a certain suppression of error. They're also used in quantum complexity theory. You may have seen quantum oracles based on random unitaries, and they are used in experimental attempts to demonstrate quantum classical separation. They're also used as models of black holes in quantum chaos at the joining point between computational information concepts and fundamental physics. And finally, we're now seeing a lot of work on quantum learning that also makes use of random unitary constructions. So you can see this review article noted at the bottom if you would like to read up more on Haar random unitaries. However, these are very hard to create for the most part. And there's a simple counting argument. It appears in the classic textbook of Nielsen and Trung. And basically the way this goes is that every quantum circuit has, by its nature, an efficient classical description. So if I take a polynomial-sized quantum circuit on n qubits, and I think about all the ways I could change that circuit, I'm going to get about exponentially many possible states it could create or possible unitaries it could implement. But there are doubly exponentially many quantum states that are approximately pairwise distinguishable. So most of them must not have efficient or concise circuits that prepare them. That would be thought that for physical processes, they would also take a very long time to form. And therefore, one could ask, are these states kind of inaccessible? And what does that mean for using Haar random states, most of which, the typical states, would be very hard to realize? So a possible solution to this problem is to construct distributions of unitaries that look uniform to an observer with some limitations or constraints. And in this case, we consider an observer who can apply a unitary in a black box way, k times, and they are going to try to guess whether this unitary was picked uniformly at random, whether it's a typical unitary from the Haar measure, or whether it's from a different distribution. And ultimately, what we'll aim to show in this work is how easy it actually is to construct unitaries that in this sense, would look Haar-typical. So as a more formal definition, I'm actually going to introduce the notion of relative error K-designs. And for this, I'll recall that there is a natural ordering on channels induced by the semi-definite matrix ordering. Sometimes we call this the completely positive ordering. So for phi and psi, 1 minus epsilon phi precedes psi if psi minus 1 minus epsilon phi is completely positive. And a more sort of physical or probabilistic way to think about it would be that psi is actually a convex combination in this case that includes phi. This automatically implies closeness in diamond norm and many other measures. Basically, any kind of convex distance will follow from this notion. So I will also introduce what I will call a k-fold weighted twirl. And if we take a measure on the unitary group, u of d in dimension d, we define this channel that picks a unitary according to that measure and applies k copies of the same unitary to some input state. So this is a d to the k dimensional space in total, but it's sort of doing a k copy type of thing. A measure is an epsilon approximate relative error k design if the weighted k-fold twirl is comparable to the par, or sort of the true unitary twirl, in both directions in this completely positive order sense. So this is also sometimes thought of as the first case statistical moments being nearly equal to those of the uniform or Haar measure. And this is a quantum analog of k-wise independence. So those of you coming more from computer science or cryptography in a classical setting may have seen this notion more commonly. And you could have some random variables. So you have n random variables. They would be k-wise independent if taking any k subset of them, the distribution of outcomes looks like an independent or product distribution. And so one could think of this as roughly saying that if you're given k samples of these random variables, it would be impossible to tell that these are not truly independent. So we're considering both a quantum version of this, but also an approximate analog. And designs are a topic that has been studied extensively. There was some work in the 2000s on these showing basically these exist, they make sense, and they're useful. And this led into a bunch of works showing that not only are these of interest, but they're not terribly hard to create. In fact, if you run random circuits in polynomial depth, so something that would be tractable for a reasonable quantum computer, maybe sort of early fault tolerant, then you would create these designs, and they're polynomial both in the number of qubits involved and also in this parameter k determining the copy number. And even more recently, this polynomial depth started to become linear. And the big idea was actually both this k and the qubit number appear as linear terms in the depth needed to reach a design. So there was now a whole bunch more papers on this, one of which will actually be the first short plenary talk, and many of which were actually presented in the Tuesday session. This is an abridged timeline. There's no way that I could cover the full extent of the literature on unitary designs unless I were given an extra hour or two. But there was still a bunch of lingering questions as to what are the ultimate limits on how shallow a circuit can be and still have a k-design property. And there was a widespread intuition and a bunch of beliefs that linear might be the best you can do, in a one-dimensional layout, and more broadly, that if you have a spatially constrained circuit in spatial dimension d, it should take about n to the 1 over d local gates to form the unitaries that make up that ensemble. And the intuition comes from light cones. It comes from this idea that if I take a little bit of information, say on one end of a one-dimensional chain or a one-dimensional circuit layout, how long does it take for that information to propagate all the way to the other end? Well, it takes about as long as the chain. And in higher dimensions, you can think about going from, say, one corner to another corner of a cube and also get sort of a related intuition. There was also some prior work showing that if you want very precise designs, in the sense of having exponentially small error or exponential precision, then you need extensive entanglement. So you need the system to be highly entangled across any cut. And you can think about, well, on a one-dimensional system, for example, if I were to cut this spin chain in half, how many gates would I need to have go across that cut before I get the two halves to be mostly entangled with each other? Well, that's also about proportional to the chain. And again, if I have more connectivity, maybe a larger spatial dimension, then this gets a little bit easier to satisfy. So this was made very rigorous in the work of Haro and Meribon, who had shown that designs in an additive norm error, so diamond norm basically, in depth n to the 1 over d, would emerge from random circuits. So this kind of matched the light cone intuition. But they followed this with a couple of open questions, noting that this didn't sort of show a converse result. And one of them was whether relative error designs are possible in sublinear depth. The other is what happens in these spatial dimensions if the depth is much shallower than basically what the light cone idea would tell you. So both of these questions, as of early 2024, still appear to be open. And our main theorem, as well as the main theorem of the concurrent merge work, begin to answer these questions. And they answer it in a surprising way. We show that in one-dimensional, or really arbitrary connectivity, as long as they're connected on n qubits, a slightly structured random circuit ensemble yields these relative error designs in depth that scales with log n. So these are very shallow circuits. Instead of linear, we're getting logarithmic depth. They are not quite the sort of uniform brickwork random circuits that are studied in much of the literature, but they're not that far from it either. You can do this with random two local gates in one dimension. And so that does show, for at least a variant of this question, that the answer is yes. It also answers sort of the analogous variant of the other open problem, that what happens in d-spatial dimensions. Well, it looks like, in our scheme at least, the spatial dimension doesn't matter that much. You get the same logarithmic dependence. In fact, in some ways, the limiting factor is the sort of error buildup and not the connectivity, not the entanglement. So how did we get to this? Well, we started with one idea to think of the design problem as a communication problem. So consider two parties, Alice and Bob, and they want to sort of form a unitary design out of joint unitaries, but they have to minimize the bipartite communication that they use to create each of these unitaries. And so one can ask, how much communication do they really need? And we considered a sort of relatively straightforward protocol in which Alice and Bob each perform local unitary twirls where they sort of average over a design ensemble on their own systems. Then they do some kind of information exchange. So they might just swap some qubits between the two systems. And finally, they again come back and twirl locally. Do they end up with a design ensemble or a design state after doing this? Well, it turns out the answer is yes. And how much communication do they need? Well, what was surprising and interesting is that it does not depend on the sizes of the local systems, at least as long as they're big enough. So they could be really, really huge, and you still only need amount of entanglement or communication that's determined by this k and the error parameter epsilon. The size never actually enters into this. So that was very interesting. It's sort of saying that the Haar or uniform ensemble would nearly maximally entangle these systems. So to create a typical unitary, one would expect to need amount of entanglement proportional to the number of qubits in each. But to look like a random unitary takes far, far less. This is something constant in the system sizes. So more mathematically, what's going on here? If you study designs for a while, you will eventually run into Schur-Weil duality. And this is this idea that a Hilbert space, a d-dimensional Hilbert space copied in a k-fold tensor product, actually splits into subspaces on which the permutations of the k copies would act non-trivially, and the k-fold unitaries would act non-trivially. So we can sort of separate the action of things that permute the subsystems and things that act on all of the subsystems, and then consider subspaces that are symmetric under one or both of those. So we could think about permutation symmetry that's going to swap the copies around, or we could think about unitary symmetry where we apply the same unitary to all of them, and some states are invariant under that. And by Schur's lemma, if an operator has the k-fold unitary symmetry, then we can write it in a particular form. So we can write it in this block diagonal form, where it is going to be a direct sum of multiplicities with sort of blocks that actually store the information. This is illustrated on the bottom. And we could also write operators of this form as linear combinations of permutation representations in this particular representation. So when we consider a bipartite protocol, we can, after the local twirls are applied, decompose operators as linear combinations of products of permutations. So these are not necessarily product states, because these coefficients don't have to be positive, and these matrices do not have to be densities, but they do give a bipartite decomposition that really only remembers the permutation information. And furthermore, following a recently published work of Harrow, we realized that inner products on this space of operators that have been pre-twirled and so have this symmetry are approximately equal to inner products of the coefficient vectors of the permutation representations. So we can basically turn this matrix problem into a potentially much lower dimensional vector problem. And so these coefficients, one of the important things again is that they live in a vector space that is, has a dimension determined by the permutation representations, depends on k, doesn't necessarily care about the local dimension d. And then, in summary, Schur-Weil duality lets us approximate or calculate spectral gaps and inner products. And what that means is that we can actually get bounds in this 2-to-2 norm sense Sometimes these are known as tensor product expanders in the design context, and these are kind of a weaker notion of design. But one of the questions then is, how do we get from this to relative error? The usual methods would sort of convert at the cost of a factor of the whole system dimension, which is, again, what we're trying to avoid. That's how you kind of get to linear depth. And in this case, we actually use a trick that has been noted in von Neumann algebras that when you have these block diagonal forms and multiplicities, the multiplicities will cancel out with the dimension of the system. And what we're left with is something that depends in a very strong way on K, but again, kind of forgets the unitary representations and their dimension, just remembers the permutation information. So that's how we get to this bipartite result, where the communication doesn't seem to depend on local dimensions. But then, how do we get from this to actually having logarithmic depth designs? Well, we consider an alternate version of this protocol, one that kind of skips the last twirl. And in this case, the information exchanging is itself a random unitary, which can be, again, approximated by unitary from a design ensemble. And we generalize this from two parties to many parties. So here we have p parties. Each of them has k copies. Each one of them does a twirl that applies the same random unitary to their k copies. And then they do a crossing twirl that's going to apply the same random unitary, k-fold, but now this unitary is crossing between systems. It's taking some qubits from each. And in the one-dimensional case, what we would finally do is start by chopping up the line into logarithmic chunks. And then we could apply these cross twirls that will combine adjacent chunks. So we just pair these up as neighbors and merge them. And then that approximates having applied a unitary chosen from a design on each of the pairs. So now we're kind of left with the same situation again, but the chunks are twice as big. And so we do the same thing. We actually can recursively build up round by round until the unitary we've applied looks like it was chosen from a global K-design ensemble. Another observation, though, is that we don't actually need to do this round by round. These merges act on distinct subsystems, and so they parallelize. So in reality, the whole thing can be sort of a two-round protocol where we do these local twirls and then do these merging twirls. And what about lattices in higher dimension? Well, they have a very analogous idea that we can take a cubic lattice, divide it into little cubes, recursively combine the little cubes, and notice that these combining operations actually parallelize. So we can do this kind of all at once, get a two-layer type thing in logarithmic depth. And there is another paper that I believe was also presented yesterday or Tuesday that uses a very similar sort of kind of decomposition scheme for, I believe, a different result, more related to complexity. One thing I want to emphasize about what we find, though, is that if you take a sort of draw a boundary through one of these systems that has become a design and count the entanglement over that boundary, you would see that the boundary cuts through sort of a number of these local or crossing twirls that is roughly proportional to its area up to some logarithmic collections. And if you're thinking from a condensed matter or physics perspective, you might realize that this means the entanglement created in this system is close to an area law. So it can't be exactly an area law. You do need these kind of log n's coming in, but you can get pretty close. And so that was one of our final realizations. In a minute, I'm going to turn over to Thomas, who will talk about some of their efforts. And one of the things kind of left by this is whether this k-dependence is optimal, and it turns out that it's not quite optimal. But before I do, I want to acknowledge some helpful conversations. We had some email exchanges with Aram Harrow and also with the other authors. I want to acknowledge the program committee and note that some of this work was also actually performed at the Beyond IID workshop. You should check that out if you're interested in information theory type things. And also acknowledge some funding for the National Science Foundation, and note our home institutions, which you should also check out. We do cool stuff. So thank you, and I will turn it over to my colleague.
Hello, everyone. My name is Tommy Schuster, and today I'll tell you about how to form random unitaries in extremely low depth. And this is based on joint work with Jonas Haferkamp and Robert Huang. So Nick already gave us a great introduction to unitary designs and his and Felix's construction of designs in extremely low depth. And so I'll start today by diving right in and presenting our construction of low depth designs. And our construction and proof differ in a number of ways from Felix and Nick's, so hopefully it's nice to see both of them. I'll then turn to the second main result of our work, which is constructing pseudo-random unitaries in extremely low depth. So in a way, this picks up where Fermi's talk on Tuesday morning left off, but I'll also provide a brief introduction to pseudo-random unitaries for those who it's helpful for. I'll then turn and briefly compare our results to analogous phenomena in classical circuits and try to convince you that this exponential reduction in circuit depth is in fact an intrinsically quantum phenomena. And then I'll discuss a few applications of our results. So let's dive into our construction of low depth designs. So I'll simply state our main result to start. So we prove that random quantum circuits form approximate unitary K designs in depth roughly K times log n over epsilon on any circuit geometry. So this is a very similar scaling to what Nick just showed you, albeit with an improved dependence on K, from quadratic to linear. And so it turns out to be fairly easy to show that this log dependence on epsilon is optimal. And we'll hear a lot from Jonas in the next talk about how this nearly linear K dependence is also near optimal. And we also provide a new proof in our work that a log n dependence is also optimal. And so our designs are optimal in all three parameters. So how do we do this? So we provide a kind of general approach for exponentially reducing the circuit depth of any construction of random unitaries. And I call it building a random unitary brick by brick. So our focus will be on this circuit here, shown on the left side. And it's a two-layer circuit, and I'll describe it as follows. So we take our n qubits, and we lay them out on a 1D line. And then we begin by grouping the qubits into roughly log n sized patches, all next to one another. And now the first layer of our circuit is we take each patch, and we apply a small Har-random unitary to it, or a small random unitary, on roughly log n qubits. And we do this to each patch with an independent random unitary in each patch. That's the first layer of our circuit. The second layer, we do the same thing, but we shift it over by half a patch. And so this produces this two-layer brickwork circuit shown here. And then we stop. That's it. And this two-layer circuit ensemble will be the focus of the rest of this talk. And I'll show that as long as these small unitaries are sufficiently random, then this big unitary on all n qubits is also random. So in a bit more detail, for designs, our main result is as follows. if we draw each small unitary from an approximate k design on log n k over epsilon qubits, then the full circuit forms an approximate k design on all n qubits. There's a small degradation of the error in this process, but this turns out not to be very important. And so we'll hear in the next talk from Jonas about how approximate k designs on Xi qubits, where here Xi is going to be log n k over epsilon, can be formed by just local random brickwork circuits in depth roughly k times Xi. So linear in k, this is kind of a remarkable result that Jonas will teach us about, and also linear in the number of qubits Xi. And we can now immediately see, using our construction, that this leads to designs on n qubits in depth k times log n over Xi. We simply double the circuit depth of each small random unitary and set Xi equals log n. And so we see we exponentially improve this dependence on n while retaining this remarkable linear k dependence that Jonas will teach us about. So how do we prove this? So our proof is actually built upon a single, pretty simple lemma, which we call the gluing lemma. So suppose I take two random unitaries, so two designs, one in blue, one shown in green, and they might act on very different sets of qubits. But suppose they overlap on a small number. And suppose I apply them in sequence, so first the blue and then the green, and our lemma states that as long as each blue and green unitary is drawn from an approximate design, then the resulting unitary is a design on all of the qubits in the support of both unitaries. And there's a small increase in the error in this process, but this increase is suppressed exponentially in the number of qubits in this overlap. And you can immediately see how, once this lemma is proven, this immediately leads to our main theorem. So we simply apply the lemma n times in a row, proceeding from left to right in this two-layer circuit. And at each step, we glue the next small random unitary into a design formed by all preceding small random unitaries. You can also see that it's a fairly versatile approach, and you can adapt it immediately to lots of different circuit geometries. Okay, so all that remains is to prove this gluing lemma, and this is kind of the fun part, and it's a part we spent a long time thinking about. And so at the beginning, we had a rather long and somewhat technical proof of this lemma, but over the last year or so, we've managed to really distill it down to just a few very easy and succinct steps. So the resulting proof is really in total about a page and a third long. And it relies on just very basic facts about Haar random unitaries. And so I'd like to describe it step by step because I'm hopeful that these steps might be independently useful for future works. So our first step is a little bit dry, but we prove a short technical lemma for bounding the relative error of a unitary design. So as Nick talked about, relative error is this very strong notion of error, and it, in general, can be kind of tricky to bound. And so for a long time, works would often use this lemma, stemming from a work about a decade ago by Brandau, Harrow, and Horodecki, which allowed one to bound the relative error. And our bound is very similar to theirs, but it improves upon it by a factor of k factorial. And this will be useful later on when I take k to be very large. Okay, on to a more interesting step. So our next step is to prove a very simple approximate formula for the average, the twirl, over a Haar random unitary. So if you've ever worked with designs or read a paper involving random unitaries, you've likely seen this formula, which is the exact formula for the twirl over a random unitary. So we imagine we have some state rho acting on k copies of our Hilbert space, and we apply k copies of a random unitary u in parallel. And then we average over u drawn from the Haar measure. And it turns out this averaging effectively projects rho onto the span of the permutation operators, sigma and tau. So here, sigma and tau are permutations between the k copies of my Hilbert space. So they live in Sk. And it turns out when we do this projection, we have to remember that the permutation operators are not necessarily orthogonal to one another. And so to properly do this projection, we need to remember this kind of numerical factor I've written in WG called the Weingarten matrix. And this Weingarten matrix just kind of keeps track of the ways in which the permutation operators are not orthogonal to one another. And if you've ever worked with this formula, you've likely been very annoyed with the Weingarten matrix, because we don't even have explicit formulas for its elements outside of very small k. We do have some bounds, but they can be kind of loose and difficult to apply. And the matrix is also signed, so you can worry about, maybe some positive terms might cancel some negative terms. So it can be kind of annoying to deal with. And so our approximate formula starts with a simple observation made in earlier works, that while the permutation operators are not perfectly orthogonal, they are approximately orthogonal when the Hilbert space dimension is relatively large. And we show that this means you can essentially forget about the Weingarten matrix and replace it with just the identity matrix. So setting sigma equals to tau in this formula above and having some constant overall factor of the dimension. And we show that this approximate formula is accurate up to exponentially small relative error. Okay. So far, I haven't told you anything about the gluing lemma. I've just told you some helpful tricks for working with random unitaries. So our last step is just to apply these tricks to the gluing lemma. So we have two random unitaries, one in blue, one in green. Applying formula 2 produces a sum over two permutations, a sigma coming from the blue unitary, a sigma tilde coming from the green. And crucially, there's a term in the expression we get, which involves when the sigma outputted from the blue unitary contracts with the sigma tilde inputted to the green unitary. And this term looks something like trace sigma, sigma tilde inverse. But I just told you that the permutation operators are approximately orthogonal when the Hilbert space dimension is large. So this trace is approximately 1 if sigma equals sigma tilde, and it's basically 0 otherwise. It's exponentially small. And so we can simply set sigma equals sigma tilde. We get the same permutation sigma on all of the qubits, and this is just the formula for the twirl over a global Haar random unitary. And this completes our proof. And again, each of these steps is basically a half-page proof, slightly shorter, once you kind of know the right way of dealing with these objects. Okay, so this completes our results on unitary designs. I'd like to now mention our second main result regarding pseudo-random unitaries. So I'll start by just recalling the definition and motivation for pseudo-random unitaries, which Firmly very nicely introduced on Tuesday. So in this whole field, designs or pseudo-random unitaries, we're trying to answer this question of when does a quantum circuit look like a Haar random unitary? And when we say look, we mean from the perspective of some observer who is performing some experiment involving this unitary U. And we're asking, is the output of this experiment the same whether U is drawn from some ensemble I'm interested in or whether U is Haar random? And as we've been discussing, as Nick introduced, a unitary K design is an ensemble of unitaries that looks Haar random in any experiment that queries U K times. It turns out, in some applications, especially in learning and cryptography, we care about experiments that query U a lot of times. So for a number K that grows polynomially in the number of qubits N. And so this motivates a second notion of when a unitary looks Haar random, called a pseudo-random unitary. And a pseudo-random unitary is a unitary ensemble that looks Haar random in any efficient quantum experiment. So any quantum experiment that queries U a polynomial number of times and also does only polynomial depth circuits in between. And so for a long time, we were not certain if PRUs even existed, or if they did, how to construct them. But on Tuesday morning, we heard of this breakthrough result by Fermi Ma and Robert Huang, which showed that, in fact, PRUs do exist and provided a proof of this fact. And so Ma and Huang show that quantum circuits can form PRUs in depth poly n in 1D circuits and poly log n in all-to-all connected circuits. So circuits still with local 2-qubit gates, but with all-to-all connectivity. And their construction really was the same construction introduced by Metger et al., which you might have heard about Tuesday afternoon. It's this PFC ensemble. To be precise, to get this poly log depth, you need a slight variant of the PFC ensemble, but the basic idea is the same. And this is shown by Ma and Huang. And so the second main result of our work is that actually we can further exponentially reduce both of these circuit depths. So we prove that local quantum circuits can form PRUs in depth poly log n in 1D circuits and poly log n in all-to-all circuits. And so these circuits are very shallow. There's a joke that log n is less than 5. So they're very shallow, they have very low complexity, and they create only short-range geometrically local entanglement. And yet we prove that they are indistinguishable from exponentially complex Haar random unitaries. So how do we construct these? Turns out it's kind of the same way we constructed low-depth designs. So we consider this same two-layer circuit, and we'll make the patches very slightly longer. So they'll be poly log n size, so just slightly bigger than log n. Then we prove that if each small random unitary is drawn from a PRU on poly log n qubits, then the full two-layer circuit forms a PRU on all n qubits. And so you can immediately see how this exponentially reduces the circuit depth. Instead of needing to perform the PFC circuit on all n qubits, we just need to perform it on poly log n qubits at a time. So how do we prove this? It turns out it's almost an immediate result of our theorem on unitary designs. So we first note that by definition of a PRU, each small PRU in this circuit is indistinguishable from a small Haar random unitary. So we might as well replace this two-layer circuit with small PRUs with a two-layer circuit with small Haar unitaries. But then we can remember that a Haar unitary is a K design with error 0 for any K, just by definition of a design. And so then we can plug this into our theorem 1, and what we get out is that this two-layer circuit with small Haar unitaries is an epsilon approximate unitary K design as long as log nk over epsilon is less than xi, the number of qubits in each patch. And so then if we take xi to just be slightly bigger than log n, say log squared n, then this is a unitary K design for any polynomial k and any inverse polynomial epsilon. So by definition of a K design, this cannot be distinguished from a Haar random unitary. And that completes the proof. So I'd like to now try to jump into a little more intuition about our results, and especially to contrast our results with what happens in classical circuits. So it turns out that there's a very, very simple argument that classical reversible circuits, so kind of the classical analog of unitary quantum circuits, require linear depth in 1D, or log depth in all-to-all connected circuits, in order to form pseudo-random permutations or designs. So the classical analogs of these quantum objects we've been studying. And the argument goes as follows. I'll just describe it now. So say we're wondering whether some classical circuit is a completely random circuit or whether it's low depth. So all we do is we take this circuit and we query it on two different inputs. And we demand that the inputs are the same on all of the bit strings except the first, where they differ. And now, if the circuit was truly random, this would produce two completely independent output bit strings. But if the circuit's low depth, a very simple light cone argument shows that the outputs have to be the same on all qubits outside the light cone of the flipped input bit. So this proves you need linear depth in 1D in order for a classical circuit to be indistinguishable from random. And so we can ask, why can't I apply the same logic to a quantum circuit? What if I take that quantum circuit and I also apply it to two bit strings that differ only on the first bit? And you can try this, and you can try to distinguish these two outputs. So one thing you can do is you can look up protocols for measuring the light cone of quantum circuits. It turns out these exist, and they proceed by basically choosing the same initial states that I've shown here. But you'll find, if you dig into it, that all of these methods scale exponentially in the size of the light cone. So as soon as this light cone becomes just above log n, these methods become super polynomially hard. You can also try something like performing a swap test to distinguish that these circuits have very low entanglement compared to a Haar random state. But then you'll find that the result of this swap test, say performed on some bipartition of the system, decays exponentially, again, in the depth of the circuit. And so in order to distinguish this, you need to resolve a very small number. And when the depth is just above logarithmic, this number is super polynomially small. So it takes super polynomially many shots to distinguish it. Finally, you could try, say, some brute force approach where you just try to learn the entire circuit. And you can look up these really nice recent algorithms for learning shallow circuits, but you'll find they all diverge exponentially in the depth. And so again, as soon as the depth is just above log, it becomes hard. And so in the end, we kind of now know the reason why all these methods diverge in the way they do. It's because quantum circuits can truly become indistinguishable from hard random at these depths. So I'll now conclude by discussing a few applications of our results. So our first application is something that PRUs are really good at, which is proving that some tasks that we'd really like to be able to perform are actually fundamentally hard. And so one task we consider is this task of quantum phase recognition. So say I give you a quantum state, and I promise you it's in one of two possible phases of matter. And I ask you to perform some measurements on that state, or many copies of that state, to try to distinguish what phase it's in. And we're going to consider a very particular class of phases called topological order. There's a whole field of research, of course, on topological order, but its defining property is that the topological order of a quantum state is invariant under any low-depth quantum circuit. And so from this defining property, we kind of immediately prove that recognizing the topological order of a quantum state is quantum computationally hard, as soon as the correlation length of that state is just slightly bigger than log n. So it grows very, very weakly with the system size. The way we do this is super simple. So we consider two ensembles of states and try to distinguish them. Our first ensemble is obtained by taking a product state and applying a low-depth PRU to it. This produces an ensemble of pseudo-random states, all with trivial order. Our second ensemble is obtained by doing the same thing, but starting with the toric code state. This produces an ensemble of pseudo-random states with topological order. Now, both of these ensembles are pseudo-random, so neither of them can be distinguished from a Haar-random state. And therefore, they cannot be distinguished from each other, and so learning the topological order of the state is computationally hard. We can also use our results to prove not just hardness, but separations, advantages for quantum learning. So the most boring way in which we do this is by simply extending many existing advantages that involve very complex Haar-random unitaries to the same advantages, but involving very low-depth quantum circuits. So as one kind of prototypical example, there's this task of trying to distinguish a Haar-random unitary from a maximum depolarizing channel. So trying to distinguish some complex coherent quantum operation from complete junk. And a few years ago, some really nice works proved that this task is hard for any classical observer. Whereas an observer with a quantum memory, so someone who can query this process, store the quantum state of that output in a memory, and then query it again and coherently couple those results, they can distinguish these two very easily. So this is an advantage for observers with a quantum memory. And so this was super nice, but at the same time, it's a little unfortunate that it only applied to exponentially deep Haar-random unitaries, since these are probably not great models for the systems we encounter in the real world. And so kind of as a joint result, first of Fermi and Roberts' work and then of ours, we now immediately have that this advantage applies even to distinguishing a depolarizing channel from an extremely low-depth quantum circuit. So something that's probably a much better model for things we see in the real world. We can also prove entirely new learning advantages entirely. So one that I like to mention involves quantum experiments with the ability to reverse time. So conventional experiments throughout the history of physics always involve forward time evolution. So we apply u equals e to the minus IHT. We might do this many times, but we only move forward. But increasingly, modern quantum experiments have the ability to actually time reverse their dynamics. So they can apply not just e to the minus IHT, but also e to the plus IHT. So not just u, but both u and u dagger. There's many ways, it depends on the microscopics of the system that you're able to do this, but there's actually quite a lot of platforms that can. And so what we prove is that these quantum experiments with the ability to reverse time can actually detect properties of many body dynamics that are completely invisible, so they're exponentially hard to detect in any quantum experiment without time reversal. We prove this even for, for a number of tasks, including some which are very physically relevant. So for example, we prove that distinguishing whether some finite time dynamics is generated by a short-range interacting system versus a system with both short-range and small long-range couplings, that this features such an advantage. So this task is hard for experiments without time reversal, but easy once you have time reversal. And so our final application is an application of low-depth designs. So it's an application jointly of our work and Felix and Nick's work. And this concerns classical shadow tomography. So classical shadows, many of you probably know it, is a very cool protocol where we can we take a quantum state and we apply a random unitary to that state and then measure. And it turns out that by applying this random unitary, we can learn a lot more about this initial state than we could with conventional measurement strategies. So the original classical shadows protocol required a deep linear depth random Clifford unitary to do this. And our results immediately imply that a log depth random Clifford circuit is just as good. So this confirms conjectures in several earlier works which introduced this idea of shallow shadows. And a simple back-of-the-envelope calculation suggests that this should open the door to shadow tomography on lots of qubits, roughly 40 to 50, say, at current noise rates. And so that concludes our results. I'd like to end with a few open questions. So to start, several kind of smaller mathematical questions regarding the optimality and generality of our construction remain open. We can also ask whether these low-depth results apply to other types of systems. For example, bosonic or fermionic or Hamiltonian systems. This seems particularly relevant for shadow and benchmarking protocols. And there's actually already been really interesting work on the implications of these ideas for quantum gravity and ADS-CFT. And so I'd like to conclude with kind of a broad set of questions, a broad direction, which I think is interesting, which starts from the observation that, or the feeling, that it's kind of surprising and maybe even a little bit concerning that quantum systems can so easily appear completely random. And so it feels important to try to understand how and where this occurs in the physical world around us. And where it does not occur, why not? And where it does, what are the implications? So I've listed a few kind of concrete, kind of first steps I think would be interesting to tackle here. But it feels like a somewhat fundamental and maybe important direction to figure out the answer to going forward. So with that, I'll conclude. Thank you all for your time and open up for questions.
We have time for questions.
So do you expect the usual brickwork circuit with log depths can also form good design?
It's a great question. My guess is yes, but I don't know how to show it.
I would also, my own mic? I would also guess yes. But yeah, it's a question.
Okay, thanks. So another question is about shadow estimation. So because this is approximate design, so you will some bias, right?
Sorry, what was the question?
And because the designs are not exact, so you will induce some bias in the estimation.
I'm not sure about that. Maybe we can talk more after.
Okay, thanks.
Yeah.
Thanks for the great work. In your work, you minimize the depth of the circuit, but in another setting, one could also consider a set of unitary and then ask whether this uniform sampling from this set approximates random unitary up to k moments or not. And then in this case, one would also want to minimize cardinality of such a finite set. But I know this is a different setting of yours, but is there some your technique or construction has some implication also in this setting, or it's still beyond the like hard to address?
Yeah, that's a great question. Yeah, so in terms of the cardinality of designs, there's lower bounds that you need at least like nk states, say, to form a state design. Our constructions have roughly like nk times log n states, because we have this overhead of log n from the depth of the circuit. So it's close to optimal, but not quite there. So yeah, it's a good open question whether you could just get nk bits of randomness.
Thank you for clarification.
Yeah.
Well, thank you for the great talk. I had a question about to Tommy about the lower bound that you said was optimal. Could you talk a little bit more about how you find this lower bound?
Yeah, great question. Yeah, so the lower bound is stating that log n depth is optimal. The way we prove it is by looking at the output distribution. If you take your unitary design, apply it to the all zero state, and measure in the computational basis. So there's this notion of the collision probability of the output distribution, so the probability for two random bit strings to collide. And we have an argument that for this collision probability to approach its Haar value, it takes log n depth. And so this was actually known already for local random circuits where every gate is independently random from some works on random circuit sampling. And we proved that it actually holds for any circuit ensemble.
Thanks.
Maybe I'll briefly say that the log n is only for 1D once you extend it to any circuit ensemble. So it could be lower for more all-to-all connected geometries.
I have a question regarding when you stitch together small PRUs into a bigger one.
Yeah.
I think at one point you said that the K designs, they're like indistinguishable from her, but for a PRU we need arbitrary many polynomial copies to be indistinguishable. So how does that work?
Yeah. So maybe one thing I glossed over is that, so when we looked at unitary designs, there was some degradation in the error. We put in some small error and we got out a slightly larger one. And a kind of similar thing happens with the PRUs in the sense that we need to put in very good PRUs that are secure against, say, sub-exponential time adversaries. And then we get out a slightly weaker PRU, which is secure against super polynomial adversaries. So you can show that this is kind of necessary to get things in very low depth. And it's also very tunable. Like as you increase the depth of the circuit, the security of the PRU we produce increases exponentially. So hopefully that kind of answers your question.
We have time for one more question.
Over here. Thank you for the wonderful talk. I apologize if this is a bit of a naive question, but I was wondering if people have looked at sort of like different convergence conditions. So like, say like you wanted to converge like weakly, so you have like some test functions that you want to converge to in that sort of class and how you could apply these techniques. I don't know if this has been like studied in the literature or if like you could apply these techniques to these types of problems. I'm not super familiar, so if you could highlight or give any insight, I would appreciate it.
So I think there's been sort of a standard approach that looks at various norms, which tend to bound lots of functions. And occasionally you do see something looking at a more specific function. So for example, anti-concentration of outputs might be one example of looking at a more particular convergent function that sometimes might converge faster than the norm distance. But maybe you also have some thoughts.
No, I kind of agree with your answer. There's lots of different notions of convergence. The relative error captures a lot of them. It like strictly supersedes them. But there are in principle even other things beyond that you could consider. Yeah.
Perfect. Thank you.
Let's thank the speakers.